let's continue our theme of defining matrix operations by looking at operations that we can do with linear vector functions. So for matrix addition and scalar multiplication, we came up with those by just working with the outputs of our linear vector functions. Since our linear vector functions produce vectors as outputs, we've sort of used up all of the vector operations we can do with those outputs, vector addition and scalar multiplication. But because linear vector functions are functions, there's one more operation that we can do with them, and that's composing the functions. That is, when you have two linear vector functions, we could take the output of one of them and put it into the input of another. So here, this left-hand side is acting like a linear vector function, right? Here the inputs are the x's and the outputs are the y's. And because we have n different outputs, n entries in this output vector, and this other linear vector function takes n inputs, we can take these n outputs from the first and put them into the n inputs to the second. So this is just a composition of vector functions. So what operation does this give us when we write down the matrices? Well, for this first one, the corresponding matrix is just the A's, A11 up through A1P, and AN1 up through ANP. And for the second matrix, this is B11 up through B1N down to BM1 over to BMN. Okay, so we're going to by doing composition of our vector functions, we're going to be defining some operation on these matrices. And I guess what we could do is just write them next to each other like this. So all our A's over here. And if we do just write them next to each other, it looks like we're defining something that we ought to call multiplication. So whatever we get by composing these linear vector functions, we will call it matrix multiplication, and we will write it this way. But what is the appropriate formula? What should go over here? Well, remember how we've been defining the result of matrix operations is we've done the corresponding thing with our system of equations, and then just we've read off the coefficients from the resulting system of equations, and that gives us the resulting matrix. So what we need to do is actually take these outputs from our first system and put them into the second system. And this is, unfortunately, it's kind of complicated looking, so it's just that the bookkeeping is complicated. Conceptually, all we're going to do is take these formulas for the y's and put them into all the y's that show up down here. Right, so simple concept, but the bookkeeping is awful just because there are so many coefficients floating around. So we're going to get B11 times Y1, and Y1, I shouldn't use a square bracket, Y1 is so it's the sum of A11x1 up through A1pxp. So I'm going to use sigma notation to write that because otherwise things get nasty if you don't use sigma notation here. So we get the sum from j equals 1 to p of A1j xj, right? So that's just this sum here, plus B12 times Y2, but right, remember there's an equation here where Y2 is the result, and that's the sum from j equals 1 to p of A2j xj, right? So the subscript on this A says we're on row number 2, but row number 2 is the row that produces y2 as its output. Okay, plus and so on. You can see what's changing as we move from term to term in this first sum. What's changing is the subscript on little a here. So the last one is going to be b1n times the sum from j equals 1 to p of a n j xj. And then this is all z1. Okay, so that's just the first line. And then, you know, as we move down to the second line and so on, all that's going to change is the coefficient of the row we're on with the b's and with the z. So, you know, the next row is going to look exactly the same, except this is going to be 2 here instead of a 1 here, 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 here. And when we get down to the last row, we're down to the row index is m. So b sub m1 times this exact same sum from j equals 1 to p, a 1 j xj, plus and so on, over to bm n times sum from j equals 1 to p a n j xj equals zm. Yes, zm. Okay, now, so we get these m equations here. Now, what we really want, so to know what this resulting matrix should be, what we need to know is what are the coefficients on the x's. But since the x's are the original input variable at the very beginning, right? We start with x's, and then we do one vector function to get y's, and then the other to get z's. So we're going from x's to z's, and that means the coefficients in this matrix should be the coefficients on the x's. But if you look at each row here, x shows up lots of times in every row, right? So what we need to do is collect up all of the terms that have x sub 1 and collect all the terms that have x sub 2 and so on. So, right, in here, in this very first term, there's an x sub 1 term that looks like b11 a 1 1 x1, right? And then over here, there's an x sub 1 term. It's b12 a 2 1 times x1, and so on up to this last term. There's a term that looks like b1n a n 1 x1. So these are all of the x1 terms in this first row. So this first, and if you look at all of them, the only thing that's changing, all of these terms have x1 times an a times a b, but it's b1 something and a something 1, right? So this first one and this last one, those are the same. And the only thing that changes from term to term is these middle numbers. But these middle numbers always match, and they're going from 1 up to n. So this first term is the sum. So here since we're going, I'm not going to use j, because j is sort of the sum that indexes these two positions. I need a new variable because I'm indexing these two positions, so I'm going to use k. So k goes from 1 to n, and it's b1k a k1, and then x sub 1. But right, all of these terms have x sub 1, so let's factor out that x sub 1 and put it over here. Okay, and then so on. When we do this for all the other variables, right, every chunk in parentheses up here has every variable in it, every x variable. So when we do this for all the other variables, let's skip forward to the x sub n terms. right? To get an x sub n out of this, we have to replace j with n. So we get b11 a1n x sub n. And then over here, again, replace j with n. We get b12 a2n x sub n. And over here, we get b1 n a n p, right? The last one here is p. I'm sorry, in this term here, so we're doing the nth variable. Sorry, there aren't n x's, there are p x's, so this should be p. Okay, and then this 1n a sub n. Now we're plugging p into here, so this should be a p as well. Okay, a n p x p. There we go. So the last x variable is x sub p. And these are all of the x sub p terms that show up in the first row. And when we gather all these together, again, they all have x sub p, so let's factor out x sub p. When we gather together all of these terms, so again, the first variable on the b and the second variable on, the first index on the b and the second index on the a, those are always the same. Right here and here. So our b always starts with a 1 and then something, and a is something and then p. And the indices in the middle always match, and they're going from 1 up to n. So we need a sum from k equals 1 to n, and k here and k there. Okay, so that's z sub 1. Now, when we do this for the other rows, you can see the only thing that changes when we move from row to row is the first index on the b's, right? So in this first row, the first index on all of the b's was 1. So when we move to subsequent rows, that just changes. So when we get down to the last row, it's the sum from k equals 1 to n of b sub m k a sub k1 times x1 plus, and so on, up to sum from k equals 1 to n b sub, so now this row index is changed to m, and then k a sub k p x sub p equals zm. Okay, and now remember, we've got the whole goal here was to get these coefficients, and now we have all of these coefficients, right? We have our starting variables, the x's, and our ending variables, the z's, and so the matrix that represents this linear vector function is just the matrix whose entries are all of these coefficients. So now we can write down the correct definition of our matrix product, right? So let me just remind myself how I had the notation set up. Okay, right. So we had all our b's and all our a's. And what this gives us is sum from k equals 1 to n of b1k a k1 up to, and then this position here, sum from k equals 1 to n b 1 k a k p. So that's the end of that row. And then down to the last row, sum from k equals 1 to n b m k a k1 over 2 sum from k equals 1 to n be m k a k p. Whew. So we did it. This is the formula for matrix multiplication. Now, this is probably not the definition for matrix multiplication that you would have guessed. Probably if I asked you to guess how we should multiply matrices, you would have guessed, well, let's just say if we have two matrices of the same size, let's just multiply them entry by entry. But we can see now that that's not the right thing to do. In some special contexts, in some topics, that operation does show up, but that is not the general definition of matrix multiplication. This is the general definition of matrix multiplication. And you can see, first of all, it's much more complicated, although we will come to understand sort of a good way to calculate this. But also, for this to even be defined, the number of, so remember we started out with B was m by n, and A was n by p, and the resulting matrix, right, it has p columns and m rows, so this is m by p. So for this to be defined, the number of columns of the first matrix has to equal the number of rows of the second matrix, right? And then the matrix product sort of uses up these values, and you end up with just the sizes on the end. Okay, so a good way to, there's one good way to summarize this whole thing. So we can write this as, so if we want to know, so this was the matrix, let's call this one B, and this one A. Okay, so if we want to write what is the matrix AB, and suppose we want to know what is the ijth entry. Well, if you look at this, the row that we're on is just the first index on B, right? And the column that we're on is just the last index on A. So if we want row I and column j, then we should do this sum, k equals 1 to n. The second index on B is k, and the first index on A is k. But the first index on B is the row index, which is I, and the second index on A is the column index, which is j. So this is the formula for the ijth entry of the product B times A. All right, so this formula is unfortunately complicated, but we will come up with good ways to evaluate this admittedly complicated definition.